Every piece of technology you interact with, your smartphone, the servers routing global internet traffic, the supercomputers tracking weather systems, speaks the exact same language. They process information using a strict binary code of ones and zeros. Because of that architecture, classical computers process data linearly. If you ask a standard machine to find a specific phrase in a massive library, it has to pull down one book at a time, read it, and move to the next. That sequential processing works well for standard math, but it hits a physical wall with highly complex variables. If you want to simulate how complex molecules fold to create targeted drugs, or map out the absolute most efficient global shipping logistics, there are simply too many paths. Even our fastest supercomputers would take millions of years to check every possibility. To solve problems at that scale, engineers realized they had to abandon the rules of classical physics entirely. The solution involved stepping down into the microscopic world, relying on the highly erratic and probability-based laws of quantum mechanics. Before any calculation can start, you need a highly controlled environment. Modern quantum laboratories look less like data centers and more like deep space engineering bays. Inside these labs sits the quantum equivalent of the standard bit, the qubit. Instead of being locked as a 0 or 1, the qubit operates entirely under quantum rules. But qubits are exceptionally fragile. A single stray photon, a trace of electromagnetic radiation, or a microscopic shift in temperature causes them to lose their quantum state, a fatal error known as decoherence. To prevent this, the initialization phase isolates the processor inside elaborate dilution refrigerators. These machines strip out external energy, cooling the chips to a fraction of a degree above absolute zero to lock the qubits into a stable starting state. Harnessing the mathematics of the universe requires researchers to first maintain absolute physical control over some of the most sensitive materials in existence. Once the system is stabilized, the computer applies specialized quantum gates. These precise pulses of energy knock the qubits out of their definitive starting positions. This animated diagram visualizes a state called superposition. While a normal bit is locked at the absolute top or bottom pole of this sphere, the qubit exists as a fluid probability distribution, occupying any point on the surface simultaneously. If you link just 50 of these qubits in superposition, the computer is now holding over a quadrillion combinations of ones and zeros at the same time. The machine is no longer reading that library one book at a time. It is processing the text of every page across the entire library in the same instant. Holding millions of solutions is useless if you cannot navigate them to find the correct one. The system solves this through a property called entanglement. By applying multi-qubit gates, the computer mathematically links the qubits. Now, the probability state of one qubit instantly dictates the state of its partners, regardless of how far apart they are. This chart shows the effect entanglement has on processing power. Because every new qubit geometrically multiplies the states of the existing network, the computing capacity scales exponentially with each addition. Entanglement provides the invisible architecture, pulling isolated, erratic probabilities into a synchronized, infinitely scalable mathematical engine. To extract an actual answer from this web, researchers run a quantum algorithm. This is a highly choreographed sequence of microwave pulses directed at the processor. This visualization shows how the algorithm uses interference. Similar to how noise-canceling headphones broadcast a reversed frequency to block out background sound, the pulses cause the incorrect mathematical paths to destructively interfere and cancel themselves out. At the same time, the algorithm forces the correct path to constructively interfere. The peaks align, heavily amplifying the probability that this sequence is the correct solution. The machine does not search for the correct answer. It shapes the math so that all incorrect paths systematically erase themselves. Throughout this entire process, the data has remained entirely unobserved, drifting in a fluid state of probability that human instruments cannot read directly. To get a usable result, we have to perform measurement. According to quantum mechanics, the very act of observing the system forces the probability phase to terminate immediately. This visualizes the final collapse. The complex, multi-dimensional wave of possibilities vanishes. Every single qubit locks into a strict, definitive state of 0 or 1. Because the algorithm already amplified the correct path, the resulting binary code has an exceptionally high probability of being the exact solution. Measurement translates the microscopic physics back into data a human can actually use. Stepping back from the microscopic scale, that mathematical output has immense stakes for modern civilization.